Hi everyone, I'm Penelope and I'm doing my presentation today on the pigeonhole principle. What is the pigeonhole principle? It's a fundamental concept in mathematics that states that if more items are put into fewer containers than the number of items, then at least one container must contain more than one or multiple items. The mathematical definition. N is the number of objects. M is the number of containers. If n is greater than m, then at least one container must contain more than one or multiple objects. So as you can see on the right, there's 9 bird boxes and 10 birds. Suppose there's 10 pigeons and only 9 bird boxes. Since there are more pigeons than bird boxes, at least one bird box must have 2 pigeons in it. Here's another example. If you have 6 slices of pizza and only 5 plates, at least one plate has to have 2 slices of pizza. Historical background. The pigeonhole principle was introduced by Johann Dirichlet in 1834. It's originally a German term for drawer principle, and it's also known as Dirichlet's box principle. Why does it matter? This principle seems simple, but it has big real-world impacts in math, science, and everyday life. It helps in problem solving, used in proofs, logic puzzles, and math competitions. It's used in computer science. It explains data compression, hashing, and network traffic. It explains real-world patterns like why people share the same birthdays or why storage runs out. Lastly, it's important in engineering. It helps with scheduling and resource management. Here's a simple proof idea. Imagine that 8 people enters a room. Each person gives at least one hug. The possible number of hugs per person ranges from 1 to 7. But there are only 7 possible hug counts, being 1, 2, 3, 4, 5, 6, and 7. Since there are 8 people but only 7 possible hug counts, at least 2 people must have given the same number of hugs. Here's how it plays in the computer science field. It explains why some things must repeat in computers. First, we have hashing. When storing data in limited slots, some data must share a spot. We have file compression. Large files shrink into fewer possible versions, so some must look the same. Lastly, we have error codes. Limited error messages mean different errors might show the same message. As you can see, this helps in storage, coding, and fixing problems in computers. Next, we have cryptography. The pigeonhole principle explains why some passwords and codes can repeat in cybersecurity. First, we have password hashing. Many passwords turn into fewer possible codes, so some must match. We have the birthday paradox, which I'm also going to get into in the next slide, more detailed. But this is finding 2 different things with the same result that happens more often than expected. Last, we have encryption. Limited key options mean different messages can end up looking the same. So what's the birthday paradox? It helps explain it. It's a surprising probability fact. In a room of 25 people, there's a 50% chance that 2 people share the same birthday. With only 365 days, but more than 25 people, birthdays must start repeating. This concept is used in cybersecurity to find duplicate hashes, also known as birthday attacks. Now, how does it play into scheduling problems? It helps solve these conflicts by showing that overlaps are unavoidable when resources are limited. So here's an example. If 8 rooms are available to book a meeting, but 9 teams need a room, at least one room has to be shared. Here's another example. If a university offers 10 time slots but only has 12 classes, at least 2 classes must be at the same time. As you can see, this helps in time management, planning, and avoiding conflicts in schedules. Now we have internet routing. This helps explain why some data packets sometimes take the same path online. First, we have limited paths. If millions of data packets travel the world through a network with fewer available routes, some must share the same path. Next, we have traffic congestion. Too many users on a limited number of servers can cause slowdowns or bottlenecks. Lastly, we have IP address conflicts. There are more devices than unique IPv4 addresses, so some must share or reuse addresses. This helps in network design, traffic control, and improving internet speed. Now, we have a strong principle example here. And the scenario is K-pop album collections. So imagine you and your friends are collecting K-pop albums or buying them. There are 5 friends, but only 4 different versions of the album available. Since 5 is greater than 4, at least one friend must have the same album version as someone else. If you pull a random photo card from a group with 7 members, there are 10 albums. At least one member's photo card will appear twice. This proves that trading is a must in the K-pop world, and I agree personally. Now we have another principle, another strong pigeonhole principle example. But a strong pigeonhole principle is a more powerful version of the basic rule. If n items are placed into m containers, then at least one container must have at least one or more items, which I said earlier. So here's the example. You have 50 photo cards and 8 albums to store them in. 50 divided by 8 is 6.5, so at least one album has to be able to hold at least 7 photo cards. Here's another example of a strong pigeonhole principle. Imagine you're watching an anime with 1,000 episodes spread across 12 seasons. 1,000 divided by 12 is 83.33, so at least one season must have 84 episodes. Even if episodes are not evenly distributed, at least one season has more than the average. This helps explain why some anime seasons feel longer than others, like those never-ending shonen arcs. For example, One Piece. It has more than 1,000 episodes. I will start it one day, but who knows if I'll finish it. Okay, now here is how the principle plays in competitions. It's often used in Olympiad and contest problems to solve unavoidable patterns. Here are a couple examples. There are 6 people in the room. Each pair is either friends or strangers. The pigeonhole principle proves that at least 3 people must all be friends or all be strangers. Here is how it can be at Hogwarts Castle, another example. So let's say that the castle has infinite dorm rooms and every single one is occupied. If a new first-year student arrives, can they still get a room? Yes. The headmaster shifts each student from n room to room n+1, freeing up one room for the new student. Even though the castle was completely full, it still had space somehow. And here's how the principle is used in careers, aka career connection. First, we have software engineering. Hashing and data storage prevents data collisions in databases and memory allocation. Load balance. It ensures efficient distribution of tasks across multiple servers. Next, we have cybersecurity. Password cracking. Attackers use it to detect patterns in password storage. Lastly, we have project management and scheduling. It ensures that tasks are distributed fairly, avoiding overloading resources. Now, my conclusion to this was that the pigeonhole principle is a simple idea with powerful applications. Thank you, everyone. And here is my sources.